Okay, so we're going to start the second part of 2.8. We left off with an exercise that to check whether these two functions, the absolute value of x and the graph 1 over x, are these one-to-one? And remember, we're going to use the horizontal line test to check whether these are one-to-one or not. So for part A, our graph is this V shape. And notice that if we draw a horizontal line here, this crosses the graph twice. Which means that if we look at this particular x value, we'll call it x1, and this particular x value, call it x2, then these have the same y value. Whatever this y value is, it's the same. So we had two different x values, but the y value is the same. So this is not one-to-one. Okay, for part A. All right, let's go to part B, which is 1 over x. So for part B, we look at the graph of 1 over x, just like so. And, well, things look a little better here. There isn't multiple crossings here. Notice, by the way, if I draw the x-axis, go through the x-axis, it doesn't cross at all, and that's okay. It's okay to not cross the graph at all. It just can't cross the graph twice or more. So here again, crosses once. So this actually is one-to-one. It passes the horizontal line test, HLT, horizontal line test. Okay, so those were the exercises at the end of the last video. What we're going to do now is define the inverse function kind of formally. So suppose f of x is one-to-one on its domain. Then f inverse exists and is defined by the following properties. So there are two properties, and we kind of did this by example at the very beginning of 2.8. That f composed with f inverse of x is equal to x, and this is for any x in the domain of f inverse, because it's first getting plugged into f inverse, and f inverse of f of x is equal to x, and this is for any x in the domain of f. And we again, if you go back to the very first example, we did this very explicitly, but essentially what is this saying? So if I have the domain of f here, so here are some x values, and then I go to f of x, then f inverse goes backwards. F inverse just takes f of x back to x. That's essentially what is being said here. So, so what we're going to do is we're going to show we're going to do some examples where we're given a function, we're going to show that it's the inverse by proving these properties 1 and 2. So for example, let's let f of x be x cubed plus 1 and g of x be x minus 1 to the 1/3 power. Remember, the 1/3 power is the same as the cube root, but I'm writing as 1/3 just because it's going to turn out to be kind of nice to write it that way. And what we're going to show, so we're going to show that g of x is actually equal to it is the inverse of f. And how are we going to do that? By showing properties 1 and 2. By showing, i.e., we're going to show that f composed with g of x is equal to x, and we're going to show g composed with f of x is equal to x. If that is true, then if so, then we know that g of x must be the inverse of f, because those are the two defining properties. Just replace f inverse with g, and if those two properties are true, then we have the inverse function. So let's go ahead and do that. Let's go ahead and do one here. So f composed with g of x. What is this equal to? Well, remember, we just rewrite f and g here. This is x cubed plus 1. G of x is x minus 1 to the 1/3 power. So this is f of g of x. So wherever we have an x in the f function, particular right here, we're going to replace that with g. So we have g of x cubed plus 1, where g of x, what is g of x? This is x minus 1 to the 1/3 power. Okay. So we substitute that in, and now we have an exponent to an exponent. We multiply exponents, and we get x minus 1 to the first power, because 1/3 times 3 is 1, plus 1. Well, that's just x minus 1 plus 1, and that equals x. So notice here that we started with the composition, and we ended up with x, so we showed this first property. So what we have to do now is go the other way. Say, okay, let's start with g composed with f, and hope that we get x this way as well. Well, this is g of f of x, where g was x minus 1 to the 1/3 power. So this is f of x minus 1 to the 1/3 power. And this is going to be x cubed plus 1, because that's what f of x is, minus 1 to the 1/3 power. Well, the 1 and the minus 1 cancel right here. And so we get x cubed to the 1/3 power. And that's x to the first power, which is x. So we started with g composed with f. We ended up with x. And that's exactly the second property. And hence we can say now that when f of x is x cubed plus 1, then then f inverse of x is equal to x minus 1 to the 1/3. By the way, I skipped actually showing you can show that f of x is a one-to-one function separately. I sort of just, I didn't do that part. But what I also want to do now, so this is one part that I wanted to show, that this is the defining property. What I also want to just take a look at is the graph of f of x and f inverse of x. So let's just take a look at that. How does it look? So let's graph f of x first. I will graph that with this white color. So you just take x cubed and it's a vertical shift, right? We just move x cubed up 1 unit. Let's do it a little bit carefully. So here's 1, and then here's -1, +1. So we have 0, 1. We have -1, 0. And then if we plug in -2, we'll get -7. Right, so 1, 2, -3, -4, -5, -6, -7. So somewhere here. And if we plug in 1, we get the value 2. So we get something like, oops. This is our, and let me label these points. So we have -2, -7. We have -1, 0. We have 0, 1. So we have 0, 1. And then we have 1, 2. So these are some points on this graph. Let's now consider the graph of f inverse, which is x minus 1 to the 1/3. So notice if you plug in 0, you'll get -1. If you plug in 1, you'll get 0. If you plug in 2, you'll get 1. If you plug in -7, you have the cube root of -8, which is -2. So what happens is, so -1, -2, 3, 4, 5, 6, and 7. So -7, -2 is right here. We have 0, -1. We have 1, 0. And then we have 2, 1 sitting somewhere here. And so you get this graph. And you can actually see kind of visually, and I'll draw this with a, if you draw the line y equals x, which is 1, 1, 2, 2, 0, 0. So we're going to draw, it's going to be something like this. Here's the line y equals x, and I haven't drawn it perfectly, but it's still hopefully visualizable. You can see this is the point 2, 1. This is the point 1, 0. This is 0, -1. And here is the point -7, -2. You can see that these are just flips. The white points in the sorry, I should have labeled those with red. Let me rewrite those in red. The points here in red, so this is the point 2, 1. It's the flip of the 1, 2. This is the point 1, 0. It flips 0, 1. There's 0, -1. And here in for the f of x, there was -1, 0. So the x and the y values are getting flipped. And that turns out to be the same thing as being symmetric, and you can see this kind of visually, symmetric about the line y equals x. So it turns out the graph, and this is true for any f and f inverse, of f and f inverse are symmetric about the line y equals x. Okay, and this is it's always going to be true because the reason is because we're always swapping x and y. This is because the points are swapped in the order of coordinates. Which means if you have, AB on the graph of f, then you have BA on the graph of f inverse. Okay? So for example, if you had 1, 2 on the graph of f, you have 2, 1 on the graph of f inverse. 0, 1 on the graph of f, 1, 0 on the graph of f inverse. And that swapping property is exactly essentially being symmetric about y equals x. So that's an important geometric property. And let me leave you guys here with an exercise. So suppose f of x is equal to 3x plus 5. And so I want you to do two parts here. So show g of x, which is the function x minus 5 over 3, satisfies two properties, that f composed with g of x is equal to x, and g composed with f of x is equal to x, i.e. g of x is actually the inverse of f. And then go ahead and graph f of x and g of x, and notice the symmetry about the line y equals x. Okay, so we'll begin the next video with this exercise, and then we'll move forward from there.